Here are a few more questions for you to practice what we learnt in parts 1 and 2. For question 1, see if you can write down the image equations based on rules you learnt at school. Some of these are intuitive and others aren't. For question 2, use what you learnt in this video series to justify your answers to question 1. Some of these will be more challenging. Pause the video now as the answers come up next. To find an image equation after reflection in the x-axis, the rule is to take the right-hand side of the original function and multiply the whole of the right-hand side by -1. In this case, we can expand this if we want to give us the answer y equals -x² minus x. To find the image equation after reflection in the y-axis, the rule is to take the original function and then replace every instance of x with -x. Expanding the brackets on the right-hand side, we now have y equals x² minus x as our final answer. To find an image equation after dilation from the y-axis by a factor of 3/4, we will first need to calculate the reciprocal of 3/4 multiplied by x. So the reciprocal of 3/4 is 4/3 multiplied by x gives us 4x/3. The image equation will be a copy of the original equation with every instance of x replaced by 4x/3. Expanding the brackets on the right-hand side gives us our final image equation, y equals 16x² 9 plus 4x/3. When the original function is reflected in the x-axis acts as a two-way mirror. Points that are on the x-axis stay put. Points that are above the x-axis get reflected below. And points that are below the x-axis get reflected above. If we now look more closely at the effect of this transformation on individual points, we see that the x values of these points are untouched, while the y values are multiplied by -1. So the point 1, 2 becomes the point 1, -2. And the point 2, 6 becomes 2, -6. And the point -2, 2 becomes -2, -2, and so on. Reflection in the x-axis affects only the y values on the original curve, so it's most appropriate to start with a version of the original function where y is the subject. Now, the image-wise are a copy of the original y's multiplied by -1. So, as before, expanding, we get y equals -x² minus x. Now a reflection in the y-axis causes the y-axis to act as a two-way mirror. As before, points that are on the mirror stay put. Points that are on the left of the mirror are reflected right, and points that are on the right of the mirror are reflected left. Once again, looking more closely at the effect of this transformation on individual points, we see that the x values of points on the original curve are multiplied by -1, while the y values are left untouched. So negative 2, 2 on the original curve becomes 2, 2. And negative 3, 6 on the original curve becomes 3, 6. And 1, 2 on the original curve becomes negative 1, 2. And so on. As reflection in the y-axis affects the x values only, starting with a version of the original function where x is the subject would be best. How did you go with this challenge? Perhaps you used your CAS to solve for x. That would certainly work. Or maybe you gave up on the method of trying to solve for x and used matrices to find an appropriate substitution instead. This works too, and proves the substitution used in question 1 was correct. I'll talk more about transformations and matrices later on. For now, let's use a pen and paper algebraic approach to solve for x. We're going to take the right-hand side of the original equation and complete the square. Taking the coefficient of x, which is a hidden 1, we halve that to give us a half, and then we square to give us 1/4. Add that result to the end of the equation and subtract to keep the equation balanced. Now the first 3 terms will form a perfect square. X squared plus x plus 1/4 is the same as x plus 1/2 squared. From here it is not so difficult to isolate the x. Add 1/4 to both sides. Take the square root. And subtract 1/2. And swap sides. Now that we have x as the subject, we know that our image x's are a copy of the original x's multiplied by -1. So all we need to do now is expand the right-hand side and rewrite this image equation with y as the subject. Expanding first, we have negative times a positive makes a negative, and a negative times a negative makes a positive. So for the first term, we just have plus or minus the square root of y plus 1/4. And for the next term, we have a negative times a negative makes a positive, so plus 1/2. Now rearranging the equation to make y the subject, we have x minus a half equals plus or minus the square root of y plus a quarter. Squaring both sides gives us x minus a half all squared equals y plus a quarter, and subtracting a quarter from both sides, x minus a half all squared minus a quarter equals y. And of course we can swap sides. Now you might be thinking, well, this looks a bit different from what we had in question 1. If you expand, you'll find that it's the same result. So expanding that bracket, we have x squared minus x plus a quarter, and minus a quarter on the end. Of course, these cancel, and there's the same result that we got for question 1. Well done if you thought of doing the question this way and managed the algebra on your own. Let's now take a look at justifying our answer for the final transformation. Dilation from the y-axis by a factor of 3/4 causes the x values of points on the original curve to be multiplied by 3/4. So the point 2,6 becomes the point 1.56, and the point -412 becomes the point -312, and the point -22 becomes -1.52, and so on. The resulting image is a horizontal squash of the original function. As dilation from the y-axis affects the x values on the original curve only, it will once again be best to start with a version of the original function where x is the subject. Taking this result from the previous question, we now have that the image x's are a copy of the original x's multiplied by 3/4. Rearranging to make y the subject, we multiply both sides by 4. Divide by 3. Add a half to both sides. Square both sides. Subtract a quarter. And swap sides. To see that this is the same result as we got in question 1, expand the brackets. We get 16x squared over 9 plus 4x over 3 plus a quarter, and we have the minus a quarter on the end. And these cancel. And here we have the same result as we got with our substitution in question 1. In this video series, we've looked at transformations that affect only the y values of points on the original curve and others that affect only the x values. When considering the effect of these transformations on rules, it is generally the ones that affect the y values only that are seen as intuitive. And those that affect the x values only are the ones that are generally seen as counterintuitive. We found that it is the way equations are usually written with y as the subject that makes the effect of these transformations look intuitive. And if we rewrote the original equation with x as the subject, the effect of these transformations is just as intuitive. In this series, we looked at a limited number of simple transformations and particular functions, which was a good way to begin exploring our problem. Following on from the work we've done, you might like to now consider these questions. Can we always rewrite a function to make x the subject? How can we justify the effect of a transformation on a rule if both the x and y values of points on the original curve are changed at the same time? And is there a way to show that the substitutions and rules we learnt at school will always work? For example, given any function at all, can we prove that a dilation from the y-axis by a factor of k produces an image function that is a copy of the original with every instance of x replaced by x over k? To make a start with these questions, you might like to watch my video on the matrix representation of transformations.